Now let's find the centroid of the solid that is bounded by z equals x squared plus y squared to the 1/4 and z equals 1. So remember that to find the centroid, we're going to have to start by finding the volume. And to do any of that, we want to start by drawing a picture of this. Now the fact that I have z is some function of x squared plus y squared is part of what hints us in that cylindrical coordinates would be useful. Because x squared plus y squared to the 1/4 really is the same thing as r squared to the 1/4. So that means that z is the square root of r. So what does that look like? Well, remember, I just draw the curve z equals the square root of y, and then kind of rotate that around the z-axis. And so you get this kind of funnel shape here. And it's capped off up here at z equals 1. Okay, so the range of z values then is from the square root of r to 1. The shadow is the intersection of z equals 1 with z equals the square root of r, which again is just the disk r equals 1. So r goes from 0 to 1, theta goes from 0 to 2 pi. So let's find the volume. The volume is the triple integral of 1 dv, and dv, remember, is r dz dr d theta when you're working with cylindrical coordinates. Z goes from root r to 1, r from 0 to 1, and theta goes from 0 to 2 pi. So on the inside, we get z times r from z equals root r to z equals 1. So that's r minus r root r, which is the same thing as r to the 3/2. Then the integral from 0 to 1 of all of that, dr, gets you 1/2 of r squared, and then 2/5 of r to the 5/2 from 0 to 1. So that ends up giving you 1/2 minus 2/5. And that's equal to 1/10. And finally, from 0 to 2 pi, we're going to integrate 1/10 d theta, which is just 1/10 of theta. And so you end up getting just pi over 5 for the volume. Okay, that's the first part. We still have to find the actual centroid, though. So the centroid, remember, is sort of it's the center of mass if we think of this as having a constant density. And since our solid has this rotational symmetry across the z-axis, I know that the centroid must lie on the z-axis. And to say that the centroid is on the z-axis is to say that the x-coordinate and the y-coordinate are both 0. So let's find the z-coordinate. The z-coordinate is 1 divided by the volume of the triple integral of z dv and I used exactly the same bounds as I used before. So z goes from the square root of r up to 1, r goes from 0 to 1, and theta goes 0 to 2 pi. So we just go through this whole thing again. The inside integral is 1/2 of z squared times r from z equals root r to z equals 1. So that's 1/2 of r minus 1/2 of r squared. Right? We square the square root of r here in the z squared and then multiply by an extra r. Then you have the integral from 0 to 1 of 1/2 r minus 1/2 r squared dr. That gets you 1/4 r squared minus 1/6 r cubed from 0 to 1. So that's 1/4 minus 1/6, which is 1/12. And finally, we have the last integral. So we're up to z bar is 1 over the volume times the integral from 0 to 2 pi of 1/12 d theta. So that's going to get you 1 over the volume times pi over 6. And let's go back up and see what the volume was. We had a volume of pi over 5. And since we're inverting it, we'll write that as 5 over pi times pi over 6. So we end up getting that z bar is equal to 5 over 6. That's a reasonable answer. We see from the picture that we drew before, we know that our solid only goes up to z equals 1, so the centroid should be somewhere between 0 and 1. And the solid is quite top-heavy, so I expect the centroid to be pretty close to the top boundary. And so altogether we found that the centroid of this solid is the point 0, 0, 5 over 6.